who do not have, yeah, especially for the students who do not have much kind of healthcare background. So actually, you saw many news, like especially lots of news in the past 2 years is mostly related to ChatGPT. What OpenAI did just now, what kind of large language model achieved some new milestone. So actually, it's not just in the general area. It's not just like you using the ChatGPT to help you to polish your email. It's not just like you using ChatGPT to answer some questions from your homework, but also it makes significant improvement and bring lots of opportunity we can use in the advanced AI technology to improve the medical area, especially to help with in the multiple angles such as diagnosis and other tasks. I will bring about more like this kind of details in the rest of today's presentation. So these kind of things bring a good opportunities. Like previously, we always ask the health and medical advice from all the doctors. But now on, we can ask something and get more easy ways to get the feedbacks from the advanced AI model. And in most kind of like situations, after the AI model become more and more powerful, it will be like more and more popular ways to ask the question directly from the AI model instead of like especially in US, you're trying to get a response from the doctor, you need to wait at least one day, even more longer time. So actually, we go back to the pathology and like radiology, this kind of area, it has already been deployed lots of AI technology, such as if you are doing study like images in general area or you study medical AI, you definitely will know the segmentation task, right? So, and the segmentation task is already be heavily used in all the like different like advanced hospitals. Definitely in some old hospitals, they didn't update their software. You cannot see that. But if you go into some like new hospital, especially they're using a very powerful computer and advanced newest software. So all these kind of medical tools already encoded the AI technology into the medical imaging analysis thing. So here are some cases. You can see the doctor already using the pathologist already using their segmentation technology to help to test the new like the medical imaging and to see help him to make a decision to see if it has already breast cancer or not. And COVID is definitely another very important case, right? In the past, COVID already 4 years ago, right? We didn't realize the time flies so fast. So start from 2020 to the 2022, that time period is very tough for everyone in the world, just because of the COVID. And as we know, in China, has a big population, and it's very challenging for people to give a fast testing for the people who maybe get infected or just to do some like a CT testing and waiting for the result from the CTs. So in general, if we're using the very like heavily testing ways, it usually take hours to get a result. But during that time, and many research study and collect data and training the AI model, and it can reduce tremendous time from hours to seconds, but also with a very high accuracy, like more than 90% accurate. You can say, oh, it's 90%. Yeah, doctor can do better, maybe 95, or some other way can do 99, even higher. But as you can see, if you are facing to do some testing for the billion of the people, especially in the COVID pandemic, 90% is good, especially we can use in few seconds to give a result for different people. And in US, FDA is it's an institution trying to give the license and permission to see what kind of technology can be used for the market. And actually, you can see this kind of diagram, right? Started from the 1993 around, Actually, there are near zero AI technology be approved by FDI and used into the real medical devices. But start from after deep learning, you can see like deep learning when start from the 2012, right? Alex Nader from Elian and Hinton and Alex. So and start from there, and more AI, advanced AI technology, including segmentation, including others, are developed and be evaluated effectively be used for help for the patients in the practical usage. So you can see from this diagram, you can see after the 2013, right? This kind of number is increased very, very quickly. So far, in every year, I didn't receive the newest data, but as you can see, since around the 2020s, every year there will be 100 kind of the technology will be used, AI technology, not others, will be used in the medical devices. That's kind of very super impressive. And we definitely heard something from Hinton, right? Hinton said, "Oh, stop training radiologists." This what he said is almost 10 years ago, right? In the 2016, while that year we have the ResNet. But so far until now, the radiology scientists, we still need them. But for their job, it's much more easier than previously, right? Due to AI, instead of replace their job, but become a more advanced assistant to help them to do more like prediction, more accurately and more efficiently. This is how the recent medical AI going. They are not trying to replace the doctor, but instead of is helping the doctor do their job better. So this is also a good ways to help. We are using all the AI tools for all our job in the right direction instead of replace the human beings, but let us to reduce 8 hours job per day to 1 hours per day. That's the goal. And after ChatGPT released, so more and more like this kind of a chatbot is released, right? So you can ask instead of ask the doctor, but we can just using the directly ask the AI chatbot. Okay, so in either you have the like Chinese, English, different kind of version. You describe what kind of symptoms you have, and then it will tell you like multiple like possible reasons, and also will give you some suggestion to see you really need to see a doctor or not. So actually, it's very important, especially in US, because in US, it's very hardly to schedule a doctor immediately. So this kind of tool in different kind of culture, country, and in different culture and in different system, it has different meanings. In some meaning, maybe you want to give the diagnosis result, but for example, in US, it will be a very good tool for the doctor and to the patient to see if that kind of symptom is too necessary to see a doctor in a short time. If that it is, we can let a doctor or let the hospital to schedule the patient as early as possible through this kind of conversation information collection system. This is very powerful and helpful. So we talk about lots of AI. What they are? Actually, AI has a long history, right? Started from 1950. We, especially in the Turing machine, they already bring the first concept of what AI it is, right? And then we were going to a statistical machine learning and applied machine learning, then going to deep learning. Nowadays, going to large language model. So it's keep changing the technology and the concepts. But mostly, before we go into talk about our model, and let me give you more information about how we can use in a deep neural network to address the different medicine problems in the history. So this is a very nice diagram made from my students. So you can see in the medical AI, there's so many different fields, and all the people has the figure here. I think it should be some fellows, even won some like a Turing Award in the history, right? So you can see actually similar as the AI's history, the medical AI also has a similar long history. It started from around 1950. Okay, and at that moment they were using a pattern recognition, right? Before computer vision, in the past, like 10 years ago, you read a book, they all call themselves pattern recognition. So they started using some like patterns to distinguish, well, okay, what kind of the medical situation it is, right? So and we have the Turing test in it, and later on, you will see the like a different like the AI technology growing, and this kind of technology all be used not only in the general area but also in the medical area. It's very nature. You just simply change the data from their like the original like traditional image or text or tabular data to some like a medical version of the mid image text vector data. But definitely medical have its special challenge, but mostly the technology could be really good to be transferred from the general domain to the medical domain in the medical. So nowadays, you can see here is the end of the technology trace. You can see we changed lots of terminology from the pattern recognition to nowadays we have a deep learning, we have the natural language processing, we have the computer vision, and especially in the natural language processing nowadays, maybe we're going to the large language model area. So in nowadays, it's very different in the past, right? In the past, like we train a model, we can using our laptop. And nowadays, like train a good model, it requires lots of parameter, huge data set. So it's changing from a mathematical research more and more going to more like applied and more engineering research, right? So we not only require the student that has a good math background, but also we require the students has a good like coding background, especially if they know some more about how to training the model more efficiently to better understand some knowledge about the GPU parallel computing would be very good for them to survive or study research in current area, right? So due to the GPU, we know that NVIDIA become the largest wealthy company nowadays. Like in 1 year, their stock is kind of 10 times than the last year. So GPU become a very, very limited resource, and this is also very important for the medical AI research study. So you can see there's something I can share with you, like since I'm from Mayo and also close worker with the Harvard Medical School. So in every lab, so their first priority nowadays, instead of recruiting one more postdoc, instead of recruiting one more doctor to help with their like labeling the data, their first priority is to set up their local server, especially medical server, for help them to training the powerful model. Such as like in Mayo, I collaborate, which the professor I collaborated, they already have like hundreds of A100 just in their one laboratory. And in Harvard, they even have the newest like H100, like 16, and A100 is about 100. So every lab has put more money and resources in GPUs to train a strong medical model, similar as how the industry train the powerful large language model. So why the medical doing that, and why we have to buy lots of GPU? Because of the deep neural network, right? After we do the investigation from the Google, DeepMind, OpenAI, they're talking about scaling law, which means you always can find that the model is larger, data is more, high quality data is more. We always can get the better performance finally. So due to that, it causing all the research recently is going this direction. Hopefully, we can have some like a super brilliant brain to change the research direction from the neural network, especially from the scaling law, to some other new direction. But in the recent, especially after ChatGPT, recent 3 years, right? Nothing is like the most powerful model, no matter from the OpenAI or from the Meta, from the Google, none of them can skip or ignore the scaling law, which they have to train a large model to to practically to using and address the real problems. So this is a similar things what we are facing in the medical area, and we are doing the same thing to trying to train the medical model larger and larger to see until sometimes it can be truly practically using to help with both patients and doctors. So in recently, if you listen some talks from the CEO of OpenAI Altman, he mentioned that there are actually three directions would be very valuable after the investigation of the large language model. The first is healthcare, and the second is education, and the third is science. So actually, I think if you are interested in something about the medical and either healthcare, it would not be a bad choice because it's definitely some right direction you should go. So we know the traditional medical AI model in the past, especially about after the ResNet, we always doing lots of things in the image classification or image segmentation. That kind of thing we always call it is called supervised learning, right? But however, like from the ChatGPT, we just realized actually it's before ChatGPT. Start from the 2018, we have the BERT from Google, and then we have the MAE from Meta, Facebook, right? So we realized that self-supervised learning is very powerful. And later on, OpenAI to train a huge GPT to tell us how powerful the self-supervised learning it is, which can beneficial from the tremendous massive data from the real world instead of to have to label every data in practice. So self-supervised learning give us better ways to do the better feature representation learning, and then can help all the like downstream tasks, either zero shot or fine tuning, achieve more better performance in practice. So in the self-supervised learning in general, we have two structure. One is BERT, right? BERT is a bidirectional like autoencoder. You will random, for example, you can see their original sentence is A, B, C, D, E. And then we will random mask some like tokens and predict this kind of random mask tokens. And the GPT, you definitely should be more familiar with this terminology nowadays because of the ChatGPT and the GPT-4 and the following kind of this model based on this technology. But the difference is compared with the BERT is it's using the auto-regressive decoder instead of using the bidirectional encoder. So auto-regressive, what's the auto-regressive mean? So actually you are random start from the start token. And after you predict the first token, the output of the first token will be used as the input as the second token as the input, and to predict the second token in the output, like this kind of auto-regressively until the last token is predicted. So compare with the BERT to do the masking and prediction, auto-regressive decoder has a little bit different mechanism to compute it. But actually, no matter BERT, BERT, or GPT, you will realize that their last terminology is T, right? So what a T is a transformer. This most fantastic framework is also created by Google. But as you see, Google created lots of fantastic technology. Either like transformer is they created, BERT is they created, right? But their model is not the smartest model. So actually, you can tell the technology to the real practical tool actually still have the gaps. So if you truly want to start this kind of like large language model things, you will realize that math is not the only thing. Even the model is not the only thing, but how to implement it in a correct way is very important. So transformer is a full size of the transformer. So in the full size of transformer, you can see there's an encoder and a decoder, right? But in the BERT, they only use the encoder, and in the GPT, they only using a decoder. And an example using the self-supervised learning is in the medical, actually they have many kind of famous work in the start from 2019. such as they have some paper called BiomedGPT, BioBird, MedBird. So mostly you can tell from the terminology is they using the technology GPT and the bird, but it feeds them into the medical or biomedical data, right? So you can see in the biomedical BioBird is they are trying to feed the bird technology into a structuralized EHR data, right? So you think about it's straightforward, but actually it's not, because EHR data is complex structure. Due to, if you look at this example, EHR data usually is time sequence data, and EHR data usually is multimodality data, and the EHR sometimes is data missing data. All these kind of special properties causing, if you're trying to pre-train the EHR data into the large model, into a transformer, it will be much more difficult than you pre-train the regular text data into the bird model. So this always brings lots of challenge while we're trying to using the existing advantage technology while we're trying to using them into the medical or biomedical area. So it'll also be the challenge in our project. So our project is trying to build a generalist model. Okay. So is it we really need, and why we need it? I will explain it in the following part. So, for example, here is a short story for Alex. Okay, Alex began with experience with painting. Then it will going to check with the dentist. Then after it get off some issue from his teeth, if he didn't feel well, he also will looking for some other people. Okay, so and such as the physical therapy and some other like a throat doctor until he finally solved his problem. And it's a real news. Okay, so in Alex's case, it's like a boy saw 17 different doctors in US, because in US we have different specialists. If one specialist cannot address this issue well, then he will refer this patient to another one. Okay, and you can see over 13 years and after over 3 years and after 17 doctors to look at one cases, and finally the problem be solved. It's kind of very time consuming, not just because of that, but also wasting lots of time, and it still bring lots of pain for the patient, like a boy, still keep suffering from the pain during the 3 years. And actually, this kind of thing could definitely be more helpful. While if we have a more generalist model, can give him a more comprehensive diagnosis, right, for multi-angle. Generalist model is not like it can only do one thing, like a specialist model, like a specialist doctor, but it should be more equipment with more like diverse knowledges, and can look at one problem from different angles and give some like draft like suggestions before they move on to see the real specialist. So this is our purpose. So we build a generalist vision language foundation model for the diverse biomedical task. So you can see in most kind of like the medical problem, like we have a longer author list, right? So lots of people want to understand it. Why we have that many authors? Because the data is limited, and the data is challenged to get and interpret it. It needs lots of different like institution to help with each other, especially we are trying to build a generalist foundation model. So such as in this work, besides ourselves, Lehigh, we also like my adjunct affiliation, Mayo Clinic. We also get much support from the Harvard Medical School, from the Stanford Medical School, from the UPenn Medical School, and the UT Health Medical School. So you can see we have like 4 or 5 different medical schools to help us to diagnosis or interpretation different data, and the different doctors to join us to do the data analysis and experiments. Finally, we have this work. So this work is not just we are running a fantastic AI model structure on some medical data, but we do a comprehensive study from the model, from the data, from the evaluation, and until the treatment evaluation, and to see this model actually give lots of potential opportunities for the future. And since we are trying to build a generalist, what means generalist it is, I will show you later. So BiomedGPT is a generalist model. And in a short sentence, it's a transformer-based model, same as GPT, same as BERT. But it can be diverse into the vision, language, and the multimodal tasks across the different biomedical modalities. And all this kind of thing will be within a single architecture. You will feel this is kind of very, very obvious after you see the GPT 4.0 and this kind of technologies. But you definitely will feel amazing if I tell you we started this project, even ChatGPT is not released. We started this project in the August in the 2022, and the ChatGPT without the vision model, the release is in the November 2022, and their first like GPT-4V is released even 1 year later in the around the November in 2023. So we are trying to build a similar functionality like the GPT-4V, but we start to do this kind of thing and finish this kind of thing several months ago before the GPT released, and 4 months before the GPT-4V released. So what it can do? It can do so many different tasks, and it can deal with so many different kind of data modalities. Okay, so tasks, it could be like a vision task, can do some like a classification, diagnosis, right? Can do some like a report generation, summarization, and this kind of thing. Even we using this to do some like real medical treatments, and although we don't feel, and all the doctors agree, we don't feel it's ready for the practical usage. But compared to all the previous kind of like we think it's a way more stupid model, or way more not that super effective like AI technology. This one, it brings some hopes for our to see if we can scale up the model, can achieve better performance on that. And meanwhile, this is not a modality specific, such as if you look at the GPT 3.5 and like 2 years ago, it only can do the NLP, like a text data, right? It cannot put it into a vision data. And even now, the current large language model, okay, if you talk about the GPT 4.0, even currently the 0.1, right? Because they are large language model. So which means they cannot put the image only. They has to put the language inside, such as I give an image, then I will give a prompt, right? Using that prompt to tell this image what kind of this model it is. But our model is a little bit different with the GPT, because I will introduce more later. So we can take the text data only, image data only, or text image data together to address the different problems. So actually, in our multimodality, we make a significant contribution. On the first step is we collect lots of data from the different tasks, and trying to replace the thousands of the specialist models which has been built in for the various kind of medical tasks. So you can see actually the transformer we just introduced, but mostly it's kind of a two sequence model, right? So we have input is a sequence. It do not have to be a language, but it has to be a token of the sequence, and the output should be a token of the sequence. So during that kind of the property, it would be good for us to build our BiomedGPT model. So what a BiomedGPT looks like, it actually looks like in this one. So this is a vanilla transformer, okay? And compared to vanilla transformer and the new model, the change in the first thing is you look at the right box, okay? So the red box compared to vanilla transformer, in the past in the transformer, they input data modality is single model. So we change this part. We make it can be adaptable for the multimodal, such as we can concatenate the text and the vision embedding with the position embeddings together as input, which is not implemented in the past kind of works. So this idea also is another general post from BiomedGPT. The original idea is from the Alibaba. One of their work is published on ICML in the beginning of the 2022. This is called OFA, Unifying Architecture from the and the tasks and the modalities through a sequence-to-sequence learning framework. Okay, so this work is trying to tell us actually we can unify in different tasks and modalities in the same model. This driven us to see if the general model can work, why we cannot using it for the biomedical data, right? So but if we just using this existing framework and didn't change anything? Actually not, because we found some like drawbacks of the OFA architecture, and we also do some architecture exploration to trying to make this kind of model become more and more like effective and powerful. So what we did change the OFA architecture to let it can do better in the biomedical data. First of all, in the vanilla transformer and the OFA, which they only using the post-normalization. So post-normalization is a very typical normalization ways, right? Just if I go to one slide before, you can see if we have the self-attention output or FFN output, then we will do a normalization here. So this is called post-normalization. So if we using the post-normalization equation, you can see this equation looks like this. Okay, we were using x plus fx. This is what residual network, right? Then we will normalize this kind of output to get a new embedding. So pre-normalization is a little bit different. We were using the xt to directly pass the normalization of the xt. So this is called the pre-normalization. So actually, in the practice, we, especially in the medical tasks, we realized that the post-normalization and the pre-normalization they do have the different like the good properties. So in the post-normalization, the good part is they can train the model more stable and more fast. But in the pre-normalization, it also has some good things. It can let the you can see these three graphs, right? So it will make the representation a little bit uncertainty and a little bit diverse the representation. So actually, it will improve the robustness and the representation ability while we're using the pre-normalization. Okay, so due to that kind of investigation, we choose to not only use the post-normalization during the training, but also plug in the pre-normalization in our training. So although you will feel it's a simple trick, but actually it can improve the model's representation learning both fast and better in the transformer. So this is the first of our innovation. Second is we change the head scale here a little bit about the training strategy. Especially we change the turning the factor of the gamma here and then make the training increase the importance of the well initialized attention heads. And through this kind of we bring additional like a hyperparameter which can help us to see, okay, which kind of the attention heads is more important and it could improve the performance of the model a little bit. And is that all about the way changing the model? Actually, it's not. So because of we realized that in the vanilla transformer and OFA, one important thing is called the positional encoding. Okay, so it is which words using to describe any two tokens distance. So we were rethinking, is the original architecture already do the fantastic and the best works in the model? Actually, we realized it's not. So we trying to adjust the multimodal data relative things. So we propose a new like a positional encoding solution. So first we call it called absolute encoding, positional encoding. Compared to the previous like more like a dynamic ways, absolute position encoding, we're using a physical ways to encoding like the positions of the word, and then we'll reduce the randomness of the positions of the word. And in addition, we also will using something called the relative position bias for the text data. So what it means, the relational bias for the text data actually is we will get the relative distance, or instead of absolute distance for any two tokens. So which can show not only for example, the null and there, it works as two. Null and pneumothorax is also is 3 or 2. It's also 2. Okay, so here may be some typo. So actually you will realize that the relative distance will bring another is the direction. Is besides of the distance is 2, but we will talk about the directions. Is something is before you or something is after you. Kind of this direction will help with the text know the different tokens relationship better, not only the distance information. In additional things is for the image data, we're not trying to put the patches to make it as a sequence of the tokens directory. As well, if we input it into the transformer, yeah, we have to put this kind of image patches, but as a sequence. But instead, we're trying to get the information between the different patches. Then we will get the 2D relative position bias for the patches, such as if this is 0, 0, and this patch will be -1, -1, and this patch will be +1, +1. This kind of new ways we can describe any two tokens distance in an image. And while this kind of information be encoded as a positional embedding, it can be better describe the token and patches relations in a 2D image. So after this kind of two like architecture changing and rethinking, then we have the new architecture used for training our model. And after the model is trained, we name it as biomedical GPT. But as you know, just we pre-train our model is because we trying to at the beginning we're trying to build a foundation. Foundation model. Although it can do multiple tasks, as what we said, it can do the image classification, language output, zero shot, few shot, it all can do. But it has, since our work is project is start beginning from the ChatGPT, we didn't using some like a fantastic technology used for training the ChatGPT. So we first in the pre-training stage, nothing changed. We are doing something similar like a ChatGPT, but our model is different, right? So we're using the whole transformer instead of just the decoder only. So this kind of architecture also is very popular in the past, such as in Google, you may heard it's called T5, and in Meta, you may heard called is BART. So both of them is trying to tell you there is architecture can using the encoder decoder as a transformer for pre-training in the same framework. So actually, we actually using the same thing and the same pre-training architecture to train the unlabeled data from the medical data. And trying to do that, we have to tell you one more thing is the transformer only can import the data from a tokens, right? So tokenization technology is very, very important. We know currently we do have better solution, but at that moment, in the text data, BPE is the best solution to tokenize, and for the image, VQGAN is the best. But nowadays we know for the image data, there are more options than VQGAN. We can transfer the visual image to the visual tokens. In addition to this two dimension, we realized that in medical data, there have lots of called bounding box concepts also could be tokenized. This is something also new. This is not something has been discussed in the past, honestly. So we're using the pixel 2 sequence to decoding this. So And something very interesting is another very famous model called the segmentation anything, right? It's a very generalist model to do the segmentation, which proposed by the Meta. So this kind of bounding box, to put into their training framework, is also used typically in this kind of generalist model. But this has these three ways called the unified vocabulary is first proposed in our work, especially for the biomedical area. So after we created the unified vocabulary, then the rest of the training would be way more easier, right? Just we get any kind of data, no matter it's image data, language data, or image language data. First is we tokenize it and make it as a sequence, and definitely we have the position embedding, right? Added into it, and we mask some tokens and predict that tokens. So all the training is like this way. And the training way, you will find that we can do the multiple ways during the training loss. We can using the GPT doing the autoregressive ways to predict all the tokens for the language data, and for the image data, we also can random masking few tokens and just predict or reconstruct the masked tokens during the training. So we call it the masked image infielding via the autoregressive way. And something also very would like to get your attention is this model. We pay tons of attentions and lots of efforts on the data collection. Just about data collection, our team spent months, I think it's at least 2 months or even more times to collect really comprehensive data, including the image. This image, you see all the data distributions from 33,000 to a few hundred data in the image, but also including very huge data in the NLP, including BioNLP, PubMed, Maker, and the Mimic 3 clinical notes. And in addition, also we collected about a vision language model data, like in multiple kind of data sets, you can see the Medicat or the deep lessons. Okay, so this is a kind of we collect a diverse kind of data set, and finally we collect around 30 more data sets and cover 25 different tasks in our works. So after we fine-tuning our model, we found in 25 of the experiment we achieved 16 of the state of the art in the diverse of the tasks. So this is maybe good, but not as good as you can feel in ChatGPT first release, right? It can beat every tasks and every models. So the reason is actually in some tasks, let's look at the data distributions. It would be help you to understanding this better. In some tasks, we do have lots of the data, and in that kind of data, if you're training a good model, it would be very, very useful and very helpful, especially the data share the similar features. Then through the pre-training, it will be very, very helpful. But in some data, as you see, like EEG or EKG, they have very, very few kind of data examples. And this kind of hundreds of data examples, and if they did not share the similar feature patterns between the data examples, then this kind of thing won't helpful to help the specific downstream tasks compared with they just using the data to train their specialist models. So far, not just our model, but if you look at the GPT-4V or even some other like LavaMed, none of this kind of foundation or multimodal large language model can achieve a good performance across various of the tasks. And so far, this model is already achieved the state-of-the-art performance, as we know. And one more thing is we want to you pay a little bit attention, but not too much. Is we also do the instruction fine tuning later, but we not originally we never planned to do that. because later on, after we finish our first model training, we start from our model training. We start our project in the August 2022, and then we start our first model training in the end of that year. Then we realize, oh, there's some ChatGPT things happening. Then we read lots of work, see why ChatGPT is good, why ChatGPT works. Then we realize that there is a paper called Instruct GPT. I think now everyone knows about it, but at that moment it's very very amazing and very make us feel excited. We found that if we using the SFT instruction fine tuning, actually can significantly align with the human intention better and to improve the language model performance better. So originally our paper first plan to submission is last year in the February. Then we choose to delay to do it until we finish the instruction fine tuning. Then we release, then it causing the delays, and we first preprint our papers in the middle of the last year, like in the May something. So although our paper is first is published preprint earlier and release GitHub earlier than the LavaMed, it should be the first like generalist multimodal model. However, just due to our submission strategy to a journal instead of a conference, causing this paper officially accepted much later than the LavaMed, but we are actually is the same time work. So after we apply the technology used for ChatGPT into our BiomedGPT, it significantly improved the language, vision language QA questions performance after we do that. So let's talk about some result and the limitation and what we will plan to do next. So first of all is you have to understand the pre-training is very, very helpful. I have to say that, and this is very people will ignore and won't realize this until we do the really comprehensive study. All the checkpoints are online. All the checkpoints you can download and you can run on your own dataset to the comparison. So Google later on in the following year, they built a model called a MedPlum model. It's a build their Plum model, and the Plum later on become the foundation technology using their Gemini. So, and you can here they have a new model called MedGemini. So actually, MedPlum model, if you look at their technical report, their 12 billion parameter performance is less than our. It's not as good as our model on all the benchmark multimodal data sets. However, you didn't realize we only have our model is only 182 million parameters compared to their 12 billion parameters. We are 66 times smaller than this kind of model, but achieve similar or even better performance. But you will ask, so in this case, why you not choose to pre-train or do something on the 12 billion model? Because actually this is some challenging things at the beginning of the launching this project. At the beginning is very few institutions to work together, and at that moment, especially before ChatGPT, we don't realize the GPU is that a very important thing. Although our lab actually is already provide like 10 GPUs to do this kind of job. At that moment, it's a huge computing resource, but it still took like months to finish the pre-training. So the pre-training is pretty slow at that moment. So actually, even with pre-training 3 versions from the small base and the large, but actually we cannot pre-training something like a billion scale of the model. Even the largest model is not achieve 1 billion. But the beneficial from this project and we are directions trying to train a larger foundation model. Nowadays, we have the hundreds of the GPUs can be accessed and like a 3B, 5B, even larger models currently training on the server. And we will see if we scale up the model's size, how much achievements we can do it. So from this, you will ask, so they using 12 billion, we're only using 182 million. Why our model can be comparable? Because they never do pre-training. This is very, very important. They just do called multimodal instruction fine-tuning, something technology just like Lava. If you look at Lava, you will realize that this is only using the post-training. The language model parameter is first pre-training on the non-medical data. Then they just fine-tuning on the medical data. It causing a significant differences compared to we pre-train on the medical data and fine-tuning on the medical data. So some similar behavior also you can find some in the mass model. So recently, if you look at O1, right? We feel O1 is amazing. OpenAI O1 is amazing, can do so much good like reasoning things and do mathematical problems. That much fantastic. But you probably will ignore another model from Alibaba is the Qianwen 2.5 mass. So that model show they just using 1.5 billion parameter, but on the math tasks, it can beat the GPT-4V. Okay, we can know GPT-4o. We can know GPT-4 at least they will took like 70 billion parameters, but Qianwen 2.5 math only using 1.5 billion parameters, but it can beat the GPT-4. So in that kind of work actually shares similar concept like ours. So a lot of things in the pre-training stage, you're already using lots of data-specific data to do this and do the good domain adaptation can actually using few parameters achieve better performance than the larger model. And here is a more comprehensive data analysis. If we without, this is about the language task, okay, and zero-shot inference. If we don't using the instruction fine-tuning like the ChatGPT did, compared to the GPT-4V, our performance is lower than the GPT-4V and much more lower, okay, on the text data. But after we using instruction fine-tuning, we can choose comparable, even one model is a little bit larger, better than the GPT-4V model. Okay, so it proves the instruction fine-tuning is much more helpful, not only on the general data set, but also in the medical data set to achieve better performance than on the language related tasks. So here are some like human evaluation. We asked the doctors from the best hospitals, as you can see, we mentioned, and we test our model, and the LavaMed is another claim the state-of-the-art model which accepted by the NERPs. And we realized from the doctor's perspective, our performance is way more better than the LavaMed, and LavaMed on many tasks is totally failed. It's just the output, some like nonsense output, honestly. But our model, on majority of the tasks, at least it can put output some meaningful or some like readable language, which impressive the doctors in the practical testing. And some discussion and future directions. So first of all, here are two very important things. First of all is you can see the medical data, right? It's super imbalanced. And that kind of imbalance causing the training is very hard to beneficial from the lots of data, and specifically can beneficial to help with all the data tasks while they only have very few data percentages in the pre-training data set. So how to address this kind of challenge is very hard. And we all know that it's like some EEG is very popular task, but actually in the world widely, EEG data example always very limited because of this kind of data collection, or have some patient need to take this kind of EEG, this kind of patient total percentage in their disease is very low rate, right? So how to address you during the pre-training or fine-tuning to address the imbalanced data is a challenge things in medical tasks. And the second thing is, I think lots of other works never didn't to do some study, because we are trying to do the multimodal pre-training, and we do so many ablation study, not only on the architecture style, but also on the data pre-training style. Then we realized something, not always like we're using all the technology together, it would be the best. And sometimes we realize that, for example, if we pre-training the text data, or if we pre-training the image data, it will hurt the performance on the text data, or it will hurt the performance on the vision language data. They are not data tasks, okay? Such as, okay, if I pre-training language, vision language, and the image, okay, then I have performance A but if I pre-training performance, for example, 90 under NLP task. But if we did not pre-training the vision data and on the NLP data, our performance will not reduce but increase to the 92%, something like that. So how to trying to adjust the training strategy in the pre-training, trying to beneficial all the data during the pre-training instead of pre-training one data hurts another data's pre-training and fine-tuning task. It's a very challenge and waiting for a good solution to address this kind of problems. We call this problem is called the negative transfer. It's more like originally we think pre-train larger data, more data is better. But due to the different data modalities, we realize that this is not always true during the pre-training, especially in the medical data. So these two challenges maybe always a long time exist, but if we can figure out a solution to address either of it, especially the negative transfer part, I think it worth at least nature machine intelligence or even better journals could be have some opportunities. So, and we also test some like zero shot tasks on this. You will realize, okay, this some task on zero shot task, the performance is super good, right? But actually, in the zero shot testing, lots of things is super imbalanced. Some task is like 95, 98. It's like very high. But in many some other tasks, we tested like 25 tasks, right? Like and in some tasks, on the average of the performance is very poor. It's not even achieved 50% of the accuracy. So it will be super annoying because if we want to truly let this kind of model be practical in the real usage, we hopefully it can do every task well instead of to do some tasks super accurate, super good, and some other tasks is super low, right? Even though you say, oh, we are the state of the art, we beat GPT-4V, even GPT-4V say, we are the state of the art, we beat all the model in the world. But if you test them, they only say 37% accuracy. So how you can be use this kind of model in practice? This will be a super challenge things in the real world. So all these kind of four things will be some tasks we are going to do in the following of our research. And if you have any ideas to know or to see any opportunities can address any of these kind of tasks, we can collaborate together. So last thing is trying to give some acknowledge and access. So we have multiple collaborators help us a lot, and we released our GitHub. Originally, before the Nature Medicine accept, actually this is 156 star. Why I keep these figures here is actually I think before and after acceptance, the impact get much kind of improved. Nowadays we have almost 500 GitHub stars. So if you are interested, go to look at it because we are not provide the code, but also give all the checkpoints. You can download from there. Also, you can download from the Hugging Face GPT, Hugging Face platform to using them directly in your tasks. You can use it as a foundation model to fine tuning. You can using it as your baseline to do a zero shot inference. Both of them work. So we also know the nature is some like a journal magazine need you pay for to reading it. So we also put the free version on the archive. But actually it's even already preprinted like 1 year ago. So if you're interested, you can read the preprint version through the archive. So thank you very much. That's all about today's talk. So if you have any question, please feel to ask.
Great, thanks, Lita. Wonderful talk. I learned a lot from you. And
Thank you.
there are 5 questions in the Q&A tab. If you click on the tab, you can see those questions.
Okay, I can see there are 5 questions, but I cannot see what the questions are. Now there are 6, I know.
Maybe
Oh,
I can read out some of
And
them.
let me stop sharing to see if I can read them. Uh,
You can click Q&A, then
yeah,
you
if I stop sharing, I can read them.
okay,
So
great.
about the challenges you faced the data sharing, could you please how you ultimately to share your data, individuals to obscure also what kind of potential solution to address this kind of medical data sharing challenge? That's a good question. So currently our model is evaluated on public data pre-trained. That's why we can share the checkpoint. But that's a very tough thing is if we using it and practical, you get some result on the private data, this kind of result cannot be shared due to the hospital policy, such as both Mayo and Harvard Medical School. If any models trained on their private data, we have no ways to get this kind of checkpoint out. In order you can think about the data out. It's not even the checkpoint cannot be outside. So I think even need many efforts. It's not just to say, oh, some research scientists can do something to address this problem, but mostly like the whole society and the government need to have the union concept to address it. And one more challenging thing is in US, as you know, all the hospitals are private company, right? They are like the Google, like the Facebook. They won't share their customer data. So it's similar thing. It's not but just because of medical has like more public health and has more like responsibilities than this kind of large tech company. So in the Obama times, he signed something to let the large hospital has to be collaborative together. So at that moment, they give lots of government give lots of fundings for the federated learning to encourage the large hospital can share the checkpoint at least between each other, but not too publicly between each other. Then can through that approach to train a better model. So GPU requirements, that's a good question. So if you go back to 2022, especially before the ChatGPT, they have very, very limited GPU. Our lab, especially that's a COVID pandemic, all the GPU are super expensive. I don't know, have you ever remembered that time period? So we spend like 50 grand by just a 10A5000. At the beginning we thought it's a much computing. We never won't be used often. But after we pre-train the model, we realized that's definitely it's far away to be good enough. But the trade-off at the beginning is we think, okay, we just train millions of the model. But later on, after 1 year later, after ChatGPT released, after Llama 1 released, we feel, oh, our model is too small. So once we submit our papers to Nature Medicine, the second step is we talk with many, many hospitals and their manager and different people. Definitely, they also see the success of the ChatGPT. So they would more investigate the GPU things. Nowadays, GPU no longer be a bottleneck for our team, but definitely for some teams still will be like require more GPUs to train the model. Currently, we don't. We have like at least 400 GPU can be easily accessed and train our model. So the question is, my question is like, if our goal is to train a model to a specific disease, such as VRM for type 2 diabetes, what do you think the most important factor of the such model to performance on the such disease? That's great. So why we using the so we before the ChatGPT released, we have well understanding about the 3 structure, including the BERT structure, GPT structure, and the T5 structure. So different structure has a different beneficial, such as BERT has the best, or BERT MAE has the best structure to do the feature representation learning. But the bad part is they have zero-shot generation ability like the GPT. And the GPT, the good part is it has a good zero-shot generation ability, but without a good representation learning ability. So recently, there are lots of work is trying to improve the representation ability through the GPT architecture. It's another thing, but mostly it depends on your model. If you want to do the domain adaptation, is through the pre-training or through the fine-tuning. So if you just trying to do the fine tuning and it could be a classification task instead of a language task, then you can just using the BERT architecture, it would be good enough to be used. And if you want to have the zero-shot like a generation, like a language generation, this kind of ability, so I strongly recommend like what we did is start it from the pre-training. And the pre-training can have the knowledge encoded in the autoregressive way, and using the instruction fine-tuning to let the output follow in the human preference would be the best option. And the next question is, how well did the task work on passing through the tabular clinical data? That's good question. So actually, we haven't do this on the tabular data because it's a very different data types compared to the vision and the language data. But in the mail and in our collaboration UPenn, they have two largest EHR data set in the world. So they all have the 10 million scale EHR dataset. So recently, due to the acceptance of this work, we already proposed the BiomedGPT in our proposal. So if that one is funded, we definitely will launch it, because you realize that if we want to launch some like large model pre-training through 10 million patients' data, in that way, it do need lots of money, scientists, and computing resource. All these kind of pieces, none of them can be missed, and we can do that kind of thing. So we haven't to do that, but if we can get some money, we already applied like $5 million from the NIH. If we can get that money, we definitely will expand our directions to the EHR data, like this kind of tabular data. And on that way, we will definitely also to collecting the instruction data to do that. So if you ask what kind of instruction data we will collect, mostly is because I have to say, trying to do a large model is not something one people can do it. We definitely need some like a team is just helping with the data. Some team is just helping with the model. And some team is just after model training, like doctor, to do the evaluation. So about the instruction data preparation, we mostly like will ask the data scientist plus doctor to do together. So actually our team already have some data scientists can help us to do that. So about the balancing across, do you think about scaling law would finding the ideal data distribution for the task? This field scaling law. So the challenge part is we want to follow in scaling law, but we cannot find the data. Instead of we don't want following the scaling law, trying to scale up the data. So in the open public medical data, the amount of the data is way less than the like the NLP data, textbook data, archive paper data. Instead of like that, in many kind of specific, like what I said, EEG image data, it's very, very limited world publicly available on the world. So instead of we can easily scale up the model, as what I said we have the GPUs, but trying to scaling up the data is a very, very challenging thing. So, and for many students, honestly, they want to learn more like technology part of things. So usually with data set collections, we usually have to ask that like some full-time employee help us, just like a data scientist, because the PhD student don't want to do that. They want to say, hey, I want to publish some like fantastic modeling papers, right? Instead of like using lots of data to help you collect your data set. So this is also another challenge. So if we're trying to do this kind of research, working with a PhD student. But unfortunately, is in hospital, our collaborator is especially like my adjunct affiliation in the Mayo. We do have tons of the data scientists and interns, which can ask them to help us to collect more data. I'm interested in the negative transferring problem. That's good. I'm also interested in trying to see how to figure it out. So could you share how you potentially tackle? Okay, this is the most challenging. If I know how to address this problem, probably I already have a plan to submit another paper to the either Nature Medicine or at least the Nature Method or Nature Machine Intelligence. It's super hard. It's super hard, especially in pre-training, because you can see in the pre-training part, lots of things is uncontrollable. So I want to get some sensing. I can share you some ideas. Is recently I get much feeling to get either from the Alan Zhu's like talks in ICR or ICML. It's which is he give a talk called the physics of language model. I don't know you have ever heard about that. Mostly it's trying to control the changeable of the data set. It's just everything is controllable. It's not like it's trying to start from training from the like Llama or some like large model, but it's just train everything through the GPT-2. But the GPT-2 is much more smaller, and everything is controllable. And to see the effectiveness first, and including there, its training data is generated, and every kind of thing can be controllable. Then during that, you can see, oh, why the negative data is happening. Then we can do that. But I have to say, in Alan Zhu Zheyuan's work, that is also much easier. Why? It's because he only studied the language data. Our things is way more complicated. Is because we study multimodality data. We have image, not talking about other modality like tabular data. Even these three types, language, and plus image only. These three data, their correlation, their negative transferring is very, very headache. If you have any good ideas or papers, please send me an email and we can work on this direction, definitely. So do you have a plan to work on explainability produced on the GPT model on the healthcare? That's a good question. So we actually have many discussions about the explainability about this kind of language model. So first of all, the language model, unlike other model, itself has the explainability. Just like we ask a language model, just it can do reasoning things, right? Just like O1, it will say, oh, the step 1, I do this, step 2, I do this, and then the problem is solved. But if you are talking about why O1 can say in these things, why a transformer can say in these things, then it's another study. It's not just about the BiomedGPT model, then it's more like to study the transformer's explainability, why this token will output this token instead of that token, right? So something also strongly recommended to let you to read the talk from Zhu Zeyuan, Alan Zhu's talk, like physics of the language model. In that kind of research direction, because everything is controllable, it naturally can give you more like explainability. So we also were trying to do something through the synthetic data, medical synthetic data for training. So in a small model to see the explainability in that angle, but not going to look at, okay, why is this mass function transformer doing this and output this token? This is another direction, very fantastic, very interesting. And I also recommend you to read a survey from my collaborators, Ning Hao, Liu, in the University of Georgia. They have called a survey called Large Language Model Explainability as a survey. So you actually, they tell you in large language model or large foundation model, they have different like interpretable as explainability things could be investigated in multiple interesting research topics. So isn't a paper a good research out? Isn't a data set paper a very good research output through? You want to say a data set could be also a good paper, right? Yes, actually, our university plus Mayo plus Harvard as three core institutions. We are now is launching a very huge project called the Biobank. We currently are trying to call the BiomedBank. So mostly it is trying to build something is like ImageNet, but not exactly ImageNet. It's more like a tool for you very easily to collect and pre-processing all the world medical data easily. We now currently focus on three data sets we're currently using in the BiomedGPT, vision only, and text only, and the vision text together. But others are waiting, such as genetic, such as tabular EHR. That's waiting. We didn't do that right now. We start from these three and trying to expanding. So final goal is we can create a web toolkit. So just like you can directly get it from Hugging Face or directly could get it from Python. You can just import your data set imported the MNIST C file or ImageNet from the Python directory. We're also trying to build a similar approach for the medical data, and then can let more people easily to study medical data without too much too much of the barrier. Actually, in our part of research, the most difficult for many computer scientists is collecting data and understanding task. So in our current one of the project is just trying to address this problem, and that work could be submitted to the best journal, Nature. In Nature, they have a Nature protocol. This kind of submission check is mostly encourage you if you do a significant contribution on data collection or toolkit development, also can submit in Nature. Okay, so this is a related conversation. This is okay. So I think all questions should be addressed. Thank you for all the questions. So if you have more, you please feel free to ask. And that's all.
Great, thanks, Lichao. It has already been like almost 12 midnight on your side. I don't want to take a lot of time. And thank you so much for giving us this amazing talk and answer all the questions from the audience. Hopefully we can foster some potential collaboration between Singapore and the US side.
Yeah, no problem. Yeah, definitely.
Yeah, thank you. Thank you, Linton. Yeah.
Thank you.
Yeah.
Thank you, everyone. Bye-bye.
Bye-bye.